Hello YouTube. Today we're going to talk about harmonic oscillation and the calculus behind it. So oscillation, the best way to visualize it or even see it in action is imagine a ball on a spring or a mass on a string, and you put force, I guess, into it, and it goes down, then it bounces right back up, and it goes down, then bounces right back up. And this motion can be graphed, and it kind of looks like this, actually. That can describe oscillation, and if you take it further, you can convert these oscillating graphs like that and make it into a repetitive cycle, and you can plot the points as time elapses of where you are at a certain point as the y's coordinates go up and down. You get the picture, literally. Okay, so another form of oscillators is biological synchrony. And biological synchrony, an example of this, is if you had an entire room of people and you told them, everybody clap at the same time. Everyone would start clapping, but it wouldn't be in sync, right? So over time, eventually everyone will start clapping. Now what is the reason behind that? Well, that's more biological, but mathematically, it's described in oscillations. And in nature, fireflies, they give off light, right? And sometimes you can see they like synchronize every time they turn on and off their flashes, and that's an example of biological synchrony, just like everyone's eventually clapping their hands at the same time, at the same rhythm. Okay, so we're going to talk about Newton's second law, but first I wanted to talk about it, and then I realized I wanted to talk about this first or later, so I'm just going to talk about this right now. So oscillations here, if you had a ball and it's rolling back and forth in this direction, a little bit of physics here, the maximum kinetic energy will be found here, and the maximum potential energy will be found on the other sides here. So that's gravitational potential energy. And if this ball keeps moving back and forth, you can figure out the oscillation. It's there. Just a little bit of things to think about. Okay, now going to Newton's second law. So as you know, the sum of the forces equal ma. M is mass, a is acceleration. But here's a question for you all. Do you trust F equals ma? Do you believe in it? And why? Well, this is known to be an empirical fact. An empirical fact, an empirical fact matches data and through tons of experiments. So if you had a ton of data points from a falling object, you could prove that it generally follows F equals ma. So technically this is, I'm not even going to write it because you could say this is technically not 100% true. I'm not saying that F equals ma is false, but you could say that, but it's not. This is what motion generally follows, but you have to be more specific because mass can change over time. So, for example, like rockets, if you're, rocket ship, right? Whoosh, you're losing fuel. That mass is changing, and that's a key component in rocket science. So this just isn't specific, is what I'm trying to say. But in general forms, you'll see it like this, and it's called an empirical fact. So let's just go a little bit into F equals ma and figure the mechanics behind it. So the derivative of mass times velocity. Now the derivative of mass with respect to time. So we have to use the rule, product rule. So the derivative of the first plus, okay, let me just do this. Okay, dv dt. There you go. So mass times the derivative of velocity. So the derivative of velocity is acceleration. So this is just accounting for that mass change I was telling you about. Mass change, could do that. When talking about the rocket as the example. And yeah, so let's move on. So Hooke's law, we're going to talk about Hooke's law. Hooke's law is spring mass motion, so going back to the ball thing here, way back here, whoosh, right? So this is the way to calculate the motion, but notice how it's second derivative here, so we'll get to the calculus behind that. But the question you should be asking yourself is, when does f double prime, or the second derivative, equal your original function? Because that's what this is, right? And if we want to figure out how to solve problems, we need to have, I guess, a way to get there. And the way to get there is to recognize similarities with basic ideas. So when does the second derivative equal the same as the function you originally took the derivative of? Well, the answer is sine or cosine. Those are like the general functions. If you take the derivative of sine, you get cosine. Okay, so let me do that. So if you take the derivative of cosine, you get negative sine. Derivative of negative sine, you get cosine and sine again if you just keep going. So I'm just going to leave it in general like this. So you take the derivative again, you get the function back. So, and that's, okay, let me go a little bit of explanation on that. That's where this circle comes from, sine and cosine. Because, sine squared plus cosine squared equals 1, things like that. So, as you get the top half, circle the bottom half, and yeah, okay. So, this is what's known as a guessing solution, and I think it's called ensemble. So, this, when you see a problem similar to this, you're going to want to use this when solving. Pretty much this there's a proof behind this. It's not too complex, but you take the derivative of what you guess the function, the general solution, that's the key, general solution. Let's put gen solution. What the general solution looks like, and then you can figure out, you can pretty much plug in the key components when you're given other pieces of information on how to solve the problem. So, oh, by the way, okay, yeah, k is a constant, spring constant. Okay, so here's the problem. We're just going to jump right into it now. Okay, so here's what you started with. So if and you're subject to initial condition, that's IC, initial condition. When t is 0, function's equal to 0, and when the derivative at that moment in time is equal to 12. So those are your two initial conditions, and the reason you need those two initial conditions is because you're starting with the second derivative. So if we're going to go back to basics here, basic calc, when you start here and you want to go way back here, what do you got to do? You got to integrate to go this way, and integrate again to go that way. And that's the reason. When you integrate, you have a constant left over. You have that plus c, and that plus c, when you're getting specific solutions, is eliminated by these two given pieces of information. So you will be given multiple pieces of information. You have to have two when you're dealing with the second derivative in order to tackle these problems. So that's the key there. Okay, so now how are you going to solve this? Well, you're going to guess. Yeah. So that's kind of how science starts off. Well, this is not technically science, but science is very similar to the stuff that you do. So anyway, you start with a guess, and then you test it, and then you can see if you can prove it. That's kind of how some science experiments start. So here we go. This was a pretty, you can see the similarities here for your guessing. And what I mean by guessing, you should kind of figure out that, oh, we were talking about everything we were in the previous slides, right? The spring constant here and Hooke's law. These look very similar, right? Hopefully you can see that. Just as a side note, you should figure out that k is equal to 9. And we know that the general solution right here is that. I'm not going to say it all, so I'm just going to use that equation here. Okay, so I wrote out the general solution that we're guessing that the original function resembles. Now this is x of t. So remember, there's x prime of t and x double prime of t. We were given, if you look at the problem, x double prime of t right there. So we're trying to backtrack, and we're guessing that the solution has some resemblance to this. And that's, again, why we need those two initial conditions. So simply plugging in k to the initial condition, to this general solution that we're assuming that the function looks like, or guessing, but we'll see if it is, would look something like this. So all I did, plugged in k, and the square root of 9 is 3. Oops. See? And so now we're going to use our initial condition found at the beginning of the problem here, where x of 0 is 0. So that's when t is 0 here. When t is 0, then we just plug in wherever t is, we plug in a 0. So let's move on to the next step. So you plug it in, and wherever you see wherever t is, you plug it in, and the sine of 0 would be 0, and cosine of 0 would be 1. So you'd be left with C2, because this would all go to 0. And your answer for the constant 2, you're solving for the constant now, C2 equals 0. Okay? So now that C2 equals 0, we're going to put that back into here, and that means that this whole thing is going to be 0. So then let's see what our solution looks like. Okay? But first, to recap, remember we have the general solution and we had our initial condition. So first we inputted what our k was and got a more specific general solution, even though it was still general. And then we used our initial condition and solved for our first constant. And our next step is to find out what our second constant is. So when we plug in c, the constant, or the second, c of 2 equals 0, then we just get the first part, because this would be plus 0. Okay? So now that we have that, and if you remember our second initial condition here, we need to find the derivative. So let's take the derivative of this, dt, and using the chain rule, you'll get our constant times cosine 3t, and since it's a chain rule, we have to multiply what's on the inside, so times 3. So it's 3 times whatever the constant is times cosine of 3t. So remember, this is our derivative of our original function, which we're trying to figure out. Now remember, our initial condition is 12, right? This is the derivative of x. It's the same thing. So let's plug that in, and this is also when time is 0. So we're going to make t equals 0, and we're also going to set it equal to 12. So that's what we're doing. Now let's actually do it. So doing that, you now you're going to try to find c1, our first constant, and that would be 12 since this goes to 1. So you'd have 3c1 12 equals 12 divided by 3 to both sides, and c would equal 4. c1 would equal 4. Okay, so now we have our first constant here and our second constant here, and we have every piece of information we need for our general solution. So you just literally take the pieces of information. So let's recap of what we have. So we have k equals 9, our first constant we found to be 4, second constant we found to be 0. And now we're just going to simply take these values and plug them in to the general equation. And so our first constant is 4 times sine square root of 9 is 3t. And then if you plug in 0, everything is 0. So your answer, this is your answer right here. And we just figured out the specific solution when using the two initial conditions to calculate our answer. So I hope this is making sense. Going back to the, in this direction, we started here, and now we're going here. You could say we started from the bottom, now we're here. This is the, okay. Anyway, so yeah. Hope this helped. I know it was a long video, but try to explain the example while going over a little bit of theory. If you want more on theory, I guess I could make another video, but you could always explore around for YouTube as well, or obviously primary sources like your teacher or something, for example, obviously. So hope this helped. Have a great day, and keep practicing.